Aromatic compounds are more stable than usual. And if that leads you to the conclusion that they're less reactive than usual, you are right. These compounds are much less reactive toward electrophiles than regular alkenes. Take a look at these chemical facts. When isobutylene is treated with bromine, this alkene adds bromine to make a 1,2-dibromide. We talked about this when we talked about the chemistry of alkenes. This happens at room temperature. On the other hand, when benzene is treated with bromine, there is no reaction. Benzenes are especially stable, so especially unreactive. You may recall that we said this reaction mechanism occurs through electrophilic addition, where the bromine becomes polarized by the double bond and has a partial positive charge and partial negative charge. And the pi electrons are attracted to that partial positive charge. A polarized bromine molecule simply is not a strong enough electrophile to react with that pi system of the aromatic ring. Why is that? Well, if a bromine electrophile adds to the aromatic ring, that aromaticity is destroyed. We can put this on a little bit more quantitative comparative basis by looking at the following reaction. In green, a reaction that does happen, I've shown the first step of electrophilic addition to this triene. Sulfuric acid is the source of a proton, a good electrophile, and a pair of those pi electrons forms a bond with the proton. This gives a conjugated carbocation, which we know is stabilized by resonance. If we look at the same reaction with benzene, we're looking at destroying the aromatic ring of that pi system to make this sigma bond. And now we have an allylic system very similar to the one up above. The top reaction in green works, the bottom reaction fails. Not because we're making something that's less stable or harder to make, but because the starting molecule is much more stable. When we look at an energy diagram to explain this, it looks like this. We're making carbocations that are very similar. So I've put them energetically in about the same place. The big difference is where these compounds start from. The triene is less stable than this benzene ring, so the activation energy for reaction with benzene is much greater. And you know that reaction rates are controlled by activation energies. So benzene is simply less reactive toward electrophiles because it's more stable. This doesn't mean that benzene does not react with electrophiles. It simply means that the electrophiles must be more powerful. And there are a few that are very common that you should learn. Take a look. Let's make a chart of electrophiles that react with benzene and the reagents it takes to make those electrophiles. If you use a reagent that is effectively Br+, that electrophile is strong enough. When bromine is put together with ferric bromide, it makes an ionic pair that is essentially Br+. This works for chlorine as well. NO2+ reacts with aromatics. We make that using nitric acid and sulfuric acid. There's a sulfur electrophile that looks like this, which we make using SO3 and sulfuric acid. You can put alkyl groups directly on the ring using carbocations. There are limitations here which we'll talk about. Not all alkyl groups work. You use an alkyl chloride plus aluminum chloride. And there's one last one that you should learn. You can attach a carbonyl group directly to the aromatic ring. If there's a carbonyl group here, in between the alkyl group and the chlorine, using an acyl chloride and aluminum chloride, we make these carbocations. The difference between these two, simply a carbonyl group is attached directly to the aromatic ring here, and then the alkyl group. Whereas in the reaction above, the alkyl group itself is attached directly to the aromatic ring. So there you have it, 6 electrophiles powerful enough to react with an aromatic ring. Let's talk more about that reaction. Here's a reaction of benzene with bromine and ferric bromide. We picture this as a bromine electrophile, Br+, with an anion. And I've drawn a resonance structure here, which I will do all the time when we talk about mechanism of aromatic compounds. So I can show a pair of these pi electrons reacting with the bromine. There's a hydrogen on this carbon as well as the bromine. And this carbon has a plus charge because it lost its pi electrons. Now when alkenes react with bromine, the second step is addition of bromide, which I'm putting in a dash for now. We're tentatively thinking about this. And we know these make 1,2-dibromides, which we picture with our arrow pushing like this. There's another option that's more favorable because it regenerates the aromatic ring, which is particularly stable. Rather than acting as a nucleophile, this bromide, or the ferric bromide anion, can take a proton, and when that happens, this pair of electrons becomes available to regenerate the aromatic ring. This is far more favored energetically, and we see that what we've accomplished is aromatic substitution. We've replaced a hydrogen with a bromine. Electrophilic aromatic substitution. A two-step reaction where an electrophile adds to the aromatic ring, disrupting the aromaticity, but then losing a proton in the second step to regenerate the aromaticity. This does not happen. Okay, so let's go back and look at our table and see what exactly the products will be for the electrophiles that we've drawn. This makes bromobenzene. This makes chlorobenzene, nitrobenzene, a compound called benzene sulfonic acid. The sulfur is attached directly to the carbon of the aromatic ring. These, of course, are alkyl benzenes. We can make some of them, not all of them. And these are acyl benzenes, aromatic ketones. And there you have it. Here are 6 electrophiles, powerful enough to react with the aromatic ring. These are the reagents it takes to make them. You should memorize those. And here are the products. These are very useful, industrially and in the research lab. In other lectures, we'll take a more careful look at the mechanism of this reaction, and we'll look at the reactions of these products, the substituted benzenes.